All right, in this video, we're going to take a look at the domain and the range of an inverse function. So we talked about domain and ranges before, and we had some examples where it might have been a little bit challenging to find, let's say, the range of a particular function. So for instance, in our domain and range section for the range of, I believe it was the last problem, was finding the range of 3 over 2x plus 5, which looking at the graph of that wasn't really that helpful because it didn't make it easy to find the y values that we would get in return. So I mentioned in that video when we got to inverse functions, we'd learn techniques to make it easier, and here we are actually in this video. So when you switch your x and your y to find the inverse of a function, not only does it reflect that original function across the y equals x diagonal line, but switching the x's and y's take their domains and ranges with them. So you also are going to switch the domain and range of the function and its inverse. So when you graph a function and its inverse, you're going to want to make sure that they are reflections across the line y equals x. And this is very important for a function like y equals x squared, where, and we'll see a similar example to this in this video, where we're going to have to not graph the entire graph of y equals x squared, but only a part of it. So it's a reflection of its inverse over this y equals x line. So again, we might have to restrict the domain and or range of our original function. So we'll see that in this video. So here's the relationship between domain and range, which might make it easier for some of the problems we talked about in the domain and range section. That the domain of our original function is going to be the same as our range of our inverse. So let's say our domain of our original function is x has to be less than 1. Well, that's also going to be the range of our inverse. Y is going to be less than 1. So remember, when we go from domain to range, we go from x to y. So the inequality that we have for our domain for f is going to be the same inequality we have for our range of the inverse. Also, the range of f, the outputs of our original function, are going to match the inputs of the inverse. So the inputs of the original function match the outputs of the inverse, and the outputs of the original function match the inputs of the inverse. So it seems kind of weird to say. We will look at, we'll create a table for these, as we'll see in the examples, to make it a little bit easier for us. But again, this is the relationship that we're going to focus on in this video, and could also help you with some of the more difficult ones in the domain and range section. All right, example 3, find the domain and range of both the function and its inverse. So we have f of x equals 5x, which we found the inverse in, I believe it was the last video, to be x over 5. So here I have the original function, a row for the domain, and then a column for the domain, a column for the range, as well as the inverse function has a space for the domain and a space for the range. And notice that these cells are colored the same way. So the domain of our original function is going to be the same as the range of our inverse. They're both yellow. The domain of our inverse is going to be the same as the range of our original function. They're both green. So they're highlighted that way to emphasize that we will have the same value in this cell will be this copy over here. We'll just change from x values to y values. That's really about it. All right, so looking at our original function, as far as the domain of it goes, there's no x's in the denominator, and we don't have any like square roots or fourth roots to worry about. So with f of x equals 5x, our domain is all real numbers. We can plug any number we want in, and we'll get a number back in return. As far as the outputs of x over 5, the original function's domain is going to match what the inverse function's range is. So for the outputs of x over 5, the inverse function, we'll get every possible number back. Now, our inverse function, we are just dividing by 5, so there's no variables in the denominator. And for our inverse function, we don't have any even roots like square roots or fourth roots. So for our inverse function, we can plug any number we want into our inverse function. We'll get a number back in return. And then we can take that value and copy it into our range value for our original function. So our original function will get back every possible number. So this just happens to have all real numbers for the domains and ranges of not only the original function, but the inverse. All right, part B, f of x equals 3x plus 2. Our original function, there's no variable in the denominator. We don't have any even roots to worry about. So we found the inverse function to be x minus 2 over 3. If not, just subtract 2 divided by 3. There you go. Our original function's domain is all real numbers. Our range, our outputs of our inverse function, the x minus 2 over 3, we will get back every possible real number in return. And then for our domain of our inverse, we don't have a variable in the denominator, and we don't have any even roots to worry about. So our domain of our inverse is all real numbers, which is going to match the output values of this original function that we started with, the 3x plus 2. So once again, we have all real numbers for the domains and ranges of the function and its inverse. All right, part C, we have g of x equals the square root of x plus 3. So now we have an x plus 3 inside of a square root, and because it's inside of a square root, the x plus 3 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 3. In our inverse function, we square and subtract. We get x squared minus 3. So our original function has a domain where x has to be greater than or equal to negative 3. And if we take a look at the graph of our original function, our lowest value of x is negative 3, and then every other value, like 1.59, every other value is going to be greater than that. So for our original function, our domain is x is greater than or equal to negative 3. That's going to be the range of the inverse function. So y is greater than or equal to negative 3 for the range of this inverse function, this x squared minus 3. And to see that, let's go ahead and graph x squared minus 3. I just called it h of x. So if we look at x squared minus 3, the lowest y value we have is negative 3, and all the other y values, like 1.516, are above this negative 3. So our range of values for this inverse function is from negative 3 up. So our range of our inverse is y is greater than or equal to negative 3. Now, if we take a look at the graphs on the same graph, notice that here's our original function in red and the diagonal line y equals x, but the graph in black is not a reflection of this red graph. There's too much going on here. So what needs to happen is we need to restrict the domain of this graph. So that way, when we do finally graph this inverse function, it is a reflection of this red graph over this diagonal line. And to do that, we're going to look at the range of this original function. So the range of the function we started with, we're starting with 0, and all of our other y values, like 0.883 and 2.015, all of our other y values are greater than or equal to 0. So for our range of our original problem, all of our y values have to be greater than or equal to 0, which means our domain of our inverse has to be x is greater than or equal to 0. And to show that in Desmos, if we go to this function and go to ABC, take these little curly braces below the V and the B, and it'll allow us to type in, here's x, and go back to my numerical pad, greater than or equal to 0. And now if we graph that, now the graph of the inverse in black here is a reflection of the graph in red across this diagonal line. So in this case, we had to limit the graph of our inverse function so it would be a reflection of the square root of x plus 3 over this diagonal line. And again, we got that by looking at the range of values of the original function. So the graph, try to graph as much as you can. There's really, no reason not to, especially if it helps you to get the right answer. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.